Continuing with pulse modulation technique. Uh, the topics to be discussed today are bipolar signaling, biphase encoding, biphase and differential Manchester coding, delta modulation, delta modulator output waveforms, limitations of delta modulation, condition for avoiding the slope overload error, adaptive delta modulation receiver, differential pulse code modulation, and there are some multiple choice questions. As we already have started with the line coding, let us recap why line coding is required, because the pulse code modulation is not sufficient to represent the signal, because pulse code modulated binary bits which are representing logic high for 5 volt and logic 0 for 0 volt, which are not sufficient when they are transmitting, when they are propagating through the channel, because they are facing several problems. The problem of recovery of clock pulses, the problem of degradation over the channel because of the uh, less noise immunity. Also, the continuous transmission of logic 1s or zeros may cause the degradation of magnitude below a threshold level, which is known as the DC wandering error. So such things may be avoided if we go for some special representation of those logic 1s and zeros, which are known as line coding technique. We already have discussed some line coding technique, and remaining part will be discussed here, out of which the bipolar signaling we will discuss today here. Now, bipolar signaling are nothing but it is showing two number of polarity for the same logic 1. That means for logic 1, if it is a half bit duration for the positive voltage for the half bit duration, uh, then it will be the negative voltage for half bit duration for the next arrival of logic 1. So similarly, alternate polarity is representing logic 1, whereas for logic 0 there is no pulse. So such a encoding technique is known as the alternate mark inversion technique, and this is very much useful for the recovery of clock, because there is a transition which is present at the middle of the bit interval. Whereas in case of bipolar not return to 0, we are representing logic 1 for full bit duration with positive pulse as well as negative pulse for full bit duration. So successive logic 1 are coming for full bit duration, but for logic 0 there is no pulse. So therefore, for bipolar not return to 0, we are getting uh, no clock recovery information at the middle of the bit interval, whereas in case of bipolar return to 0, there is a half bit duration transition which is providing the receiver a clocking information, so that separate local oscillator is not required at the receiver, because this information will have the clocking information which will be required in case of recovery of the signal at the demodulator. Now, bipolar signaling are having some advantages, because it is occupying low bandwidth than the unipolar and polar not return to 0. This technique is suitable for transmission over AC coupled lines because there is a transition. That is why it will not be wandered. So DC wandering can be avoided, as the signal is dropping does not occur here. A single error detection capable is present in this coding technique, but for the disadvantage we have the long strings of data causes loss of synchronization. So such cases we have to think about some other technique of coding. So the biphase coding are another type of line coding technique, which are categorized into two types. That is the biphase Manchester coding and differential Manchester coding. The biphase Manchester coding is showing that logic 1 can be represented for half bit duration positive pulse and half bit duration negative pulse. So one bit duration is divided into positive pulse and negative pulse. So such a representation is done for logic 1, but for logic 0 there is a negative half bit duration pulse followed by positive half bit duration pulse. So therefore such a encoding technique, that is a biphase Manchester coding technique, does have the clocking information as well as the noise immunity is very high because the signal excursion is starting from negative voltage to positive voltage, as well as DC wandering can be easily avoided because there is a transition at the middle of the bit interval, whether it is a logic 1 or logic 0. And there is a differential Manchester coding. So if we go to the next slide, both the waveforms are shown. That is for differential Manchester coding. We are seeing there is a transition which is a falling edge transition for logic 1, and thereafter there is a 0 logic 0. For the logic 0 there is again a falling edge transition, but when there is a 0 to 1 transition in the binary bit, at that time there is no transition in the differential Manchester coding. So 0 to 1 transition is not sensed, but when there is a 1 to 0 transition, then only there will be a falling edge. Now delta modulation is one of the important modulation technique utilized for digital modulation conversion, in which the input analog signal is taken and which is applied to the subtractor. The subtractor subtracts the input message signal with the quantized previous quantized magnitude. Now if this comparison is positive, then it is creating a positive error voltage, and if the difference is negative, then it is producing small amount of negative error voltage. Thereafter there is a limiter and sampler. They are producing either plus or minus voltage, but a fixed quantity of magnitude is produced. This is known as error voltage, which is approximated to either positive step size or negative step size. So uh, this is the important part of the delta modulation, uh, which which is telling that limiter followed by sampler is producing a 1-bit quantizer. So such a 1-bit quantizer device produces either a positive pulse or negative pulse depending on the error positive or negative, and whatever is the quantized error that has been transmitted as delta modulated signal and also fed back to the accumulator circuit so that it will generate the previous quantized level. So the feedback circuit is nothing but a accumulator or integrator that will accumulate all the step sizes, that means the positive errors or negative errors. So these accumulated errors will be forming the staircase waveform, and they are compared again with the input message signal so that the next error can be generated. Now this is the typical output waveform for delta modulated signal, in which it is clearly showing that sometimes the approximated magnitude is exceeding the slope of the message signal, and sometimes it is falling back to the slope of the message signal. So therefore sometimes errors are more positive and sometimes errors are more negative. So such a approximation error exists in case of delta modulation, which could be minimized by some mathematical conditions, which will be shown in the signal to noise error calculations. Now there are limitations of delta modulated signal are twofold. That is, one is the slope overload error and the second is the granular noise. Normally a message might have great fluctuation of the message magnitude. So at that time what will happen, if the approximated staircase waveform is produced, it may fall below the message slope. Therefore continuously the message slope is exceeding the staircase waveform. Therefore positive therefore for successive samples the amount of quantization error is always unipolar. So unipolar error is not expected. The error may be oscillating between the positive or negative if the slope is properly followed by the quantized signal. But if the slope is not properly followed by the quantized signal, then the error might be unipolar, and such a unipolar error produces the slope overload error, That means the slope of the message is not properly followed by the staircase waveform. And there is another type of noise which is known as the granular noise. The granular noise are nothing but the flatter portion of the message signal for which the staircase waveform uh, oscillates over the uh, flatter portion of the message signal. That is why there is always a fluctuation of the quantized signal to follow the flatter portion. So that is why for the steeper portion we need a higher step size, and for the flattest portion we need a smallest step size. So therefore we need a compromise between the two, so that a message signal could be properly followed by the delta modulated signal. So this is the condition to avoid the slope overload error by the delta modulated signal. This is showing the maximum slope of the message signal should be less or equal to the slope of the delta modulated quantized waveform, because delta modulated signal is nothing but the approximated error, but accumulator produces the quantized signal. So those quantized signal might have a slope which is s by t. S is the height of the step size and Ts is the duration of the sample. So S by Ts is the quantized slope of the quantized signal. So that should be higher compared to the maximum slope of the message, so that the slope of the message may be properly followed to reduce the slope overload error. This is the adaptive delta modulation. In case of adaptive delta modulation, there might have a variation or fluctuation in the message magnitude that is not same in all the time duration of the message signal. That is why we need the quantized signal. That means the staircase waveform, the step size should vary with reference to the fluctuation of the message sample. So that is why adaptive delta modulation is produced. So in this case, similar to the data modulator, a subtractor block is present at the beginning. Thereafter, limiter followed by sampler. That is also 1-bit quantizer, and the output is again fed back to the feedback network, in which there is a accumulator circuit followed by integrator. So here the accumulator circuit is fed by the sampler output, so that the step size may be varied according to the fluctuation of the message slope, so that slope overload noise may be easily avoided. This is the adaptive delta modulation receiver. In the adaptive delta modulation receiver, we are seeing that the input, that is the modulated signal, is applied, as well as it is fed to the logic for step size control before being multiplied. And after the multiplication, we are getting the higher frequency and lower frequency component, which will be added to the adder with the output delayed and fed to the same circuit adder, so that the combination will be low pass filtered and we can get the output. So therefore the adder in the output in the circuit represents the accumulator. So it will accumulate all the successive step sizes, and that will be producing the quantized signal, which will be low pass filtered to produce the slope of the equivalent message signal, and that will be the actual output which we desire. This is the differential pulse code modulation encoder and decoder. For the differential pulse code modulation, we need to predict the sample, that means predict the quantized signal which will be compared with the message signal. So differential pulse code modulation and delta modulation has only one difference. In case of delta modulation, we have seen that the subtractor at the beginning of the modulator compares the present sample and previous quantized value, whereas in case of differential pulse code modulation, an intelligent feedback network system predicts the sample which is compared with the present sample, and if there is an error, that will be quantized by a 1-bit quantizer, and that will be fed to the entropy coder for channel output. The receiver will have the first stage entropy decoder, and that will be fed to the similar accumulator circuit, which are also employing predictor. Therefore finally we are getting the output which is proportional to the message signal. Therefore, the differential pulse code modulation is the difference in the amplitude of two successive samples is transmitted rather than the actual sample, because the range of sample differences is typically less than the range of individual samples. Fewer bits are required for DPCM than the conventional PCM. Now there are some multiple choice questions are given here. The first is telling that which of the modulation technique is digital in nature: pulse amplitude modulation, pulse position modulation, delta modulation, or none of these. Obviously, delta modulation is a digital modulation technique. Quantization noise occurs, in which case PAM, PWM, DM. Obviously, in case of delta modulation, because quantization process is a digital modulation technique, PAM and PWM is an analog modulation technique. Therefore, there is no chances of quantization for PAM and PWM. So obviously, the answer is C, delta modulated signal. The third is telling that the standard data rate of PCM voice channel is 8 kbps or 8 bit per second, 16 kbps or 64 kbps. So this is, I will tell that if you go through the uh, normal market study, then you can easily answer to this question. So question number 3 is the homework that you have to answer. Pulse amplitude modulated signal can be detected using a low pass filter or band pass filter, high pass filter, or band stop filter. We already have seen that low pass reconstruction filter is a type of low pass filter which is responsible for the detection of pulse amplitude modulated signal, because pulse amplitude modulated signal are nothing but the train of impulses or train of rectangular pulses whose magnitude is varying with respect to the message magnitude or instantaneous message information. So if it is low pass filtered, then the slope of the message will be extracted from the pulse amplitude modulated signal, and we can get the received signal proportional to the incoming information. The combination of compressor and expander is called a compander. We already have seen that if there is a uh, fluctuating message signal, that could be passed through a compander, so that before being encoded, it might have a finite number of maxima and minima, or finite level of minima and maxima. The non-uniform quantization leads to reduction in transmission bandwidth, increase in maximum signal to noise ratio, increase in signal to noise ratio for low level signals, simplification of quantization process. So let us go through some uh, more slides in the next class, so that these questions you can answer by yourself. In the next slide, there are some more questions. That is, alternate mark inversion signaling is also known as the bipolar signaling, Manchester signaling, polar signaling, or unipolar signaling. It must be bipolar return to zero signaling, because in case of alternate mark inversion, we already have seen it is a half bit duration positive pulse and half bit duration negative pulse for alternate number of appearance of logic 1. What is the Nyquist rate for sampling the signal represented by the message frequency sine of 200t plus sine of 400t? Normally, the message signal may be a superposition of multiple sinusoidal signals, but the signal is having the highest frequency component you have to find out. So here, the 400t might have the highest frequency component. So once we are getting the frequency value of this sine 400t, because we know 2 pi f t, so t is present here, so 2 pi f is equal to 400, so f is equal to 400 by 2 pi. So frequency residing in sine 400t is 400 by 2 pi. If we multiply it by 2, that is 400 by pi is the maximum frequency. So therefore we can easily calculate what is the sampling rate, because 2 times of the message frequency is the sampling frequency. The compounding is used to overcome the quantization noise in PCM to in PCM transmitter to allow amplitude limited in the receiver, to protect the small signals in PCM from quantization noise, in PCM receivers to overcome impulse noise. So which one is true? So compounding is used actually to reduce the fluctuation of the magnitude. So if the fluctuation is reduced, then only the error approximation could be reduced. So therefore, to overcome the quantization noise in PCM may be the answer for the question number 10. Nyquist rate for sampling a signal representing xt is equal to sine of 200t and sine of 400t product is what? So sin A sin B formula can be converted into cos A minus B minus cos A plus B. So that will be having highest frequency component cos A plus B. That is 200 plus 400 gives you 600t. If we divide 600 by 2 pi, then it is giving 600 by 2 pi as the message frequency. So therefore sampling rate means we have to multiply it by 2. So that will be 600 by pi. Therefore option D is the correct answer.